Whether neural information processing is entirely classical, or whether it involves quantum mechanical effects, remains one of the most profound open questions in science. For decades, the idea that quantum phenomena might play a functional role in the brain has sparked intense debate. Early proposals, like Penrose and Hameroff's Orch-OR theory, suggested that quantum coherence in microtubules could underlie consciousness. But these ideas faced strong criticism, primarily because of the extreme difficulty of sustaining quantum coherence in warm, wet, noisy biological environments. Decoherence times were thought to be far too short for any meaningful quantum computation in the brain. Yet recent advances in quantum biology have reignited interest. We now know that quantum coherence can persist in photosynthetic light harvesting complexes, enabling near-perfect energy transfer efficiency. Similarly, the radical pair mechanism in bird magnetoreception suggests that quantum effects may mediate biological sensing at physiological temperatures. These discoveries challenge the assumption that quantum effects are incompatible with biology, and they open the door to the possibility that similar mechanisms might exist in neural systems. But how do we test this? Traditional approaches have focused on searching for quantum coherence or entanglement in specific biophysical substrates, microtubules, ion channels, or membrane proteins. But such searches face fundamental challenges. They require detailed knowledge of microscopic dynamics, are extremely sensitive to noise, and often lack clear experimental signatures. Here's a new perspective. Instead of asking where quantum effects might occur, we ask what kind of information processing would be impossible to explain classically, regardless of the underlying physics. This is the core idea behind our work. A model-agnostic, information-theoretic test for nonclassicality in neural representations, using autoencoders as a transparent framework. Autoencoders are a foundational concept in machine learning. They compress high-dimensional data, say, images or neural activity patterns, into a low-dimensional latent space, then reconstruct the original input from that compressed form. The latent variables represent a distilled, efficient representation of the data. This mirrors a core principle in neuroscience. The brain likely uses compact, hierarchical representations to process vast amounts of sensory input under strict energy constraints. Now here's the key insight. If neural systems were to exploit quantum advantages in computation, it would most plausibly happen in the encoding and compression stages, where information, energy, and entropy must be managed efficiently. So rather than look for quantum states in neurons, we ask, can the structure of the brain's latent representations be explained by classical probability theory? To test this, we introduce a bell-type consistency test in latent space. Think of it like this. Imagine you have a system that produces outputs under different readout contexts, like measuring different observables in a quantum system. In a classical model, all these outputs should be explainable by a single, positive probability distribution over hidden variables. Here, the latent representation. But if that's impossible, if the statistics across different contexts cannot be jointly described by any such classical distribution, then the system exhibits non-classical behavior. We formalize this using a linear non-classicality witness. Given multiple decoder settings, we estimate the observable output statistics. These are concatenated into a vector, and we ask, can this vector be written as a convex combination of projections from a single positive latent distribution? Mathematically, we define a forward matrix A, which maps latent distributions to observable outcomes. The set of all classically allowed statistics forms a convex polytope C equals backslash. A W backslash mid W backslash Jec 0, backslash sum Wi equals 1 backslash. A witness vector C defines a scalar statistic S, P, equals C backslash C dot P. For any classical model, S, P, backslash like backslash max I C backslash C dot AI dollar, where AI are the columns of A. If we observe S, P, backslash max I C backslash C dot AI dollar, we violated classical consistency. We define backslash delta equals backslash max backslash C backslash 2 equals 1 backslash delta C dollar, where backslash delta C equals C backslash C dot P as backslash text CL C. A positive backslash delta certifies non-classicality in the ideal case. Now, in real experiments, noise is unavoidable. So we model a gradual degradation. The observed statistics are a mixture of ideal non-classical statistics PQ and a classical distribution P backslash text CL, interpolated by a parameter backslash alpha. P backslash alpha equals 1 backslash alpha, PQ plus backslash alpha P backslash text CL. When backslash alpha equals $0, we're in the ideal non-classical regime. When backslash alpha equals 1, everything is classical. We also include additive Gaussian noise backslash Roman 11, so the observed data is P backslash text obs equals P backslash alpha plus backslash Roman 11. The witness value becomes S backslash text obs equals C backslash C dot P backslash text obs dollar with mean backslash mu backslash alpha 1 backslash alpha C backslash C dot PQ plus backslash alpha S backslash text CL and standard deviation backslash sigma S equals backslash sigma backslash C backslash 2. Detection of non-classicality occurs when S backslash text obs S backslash text CL plus backslash kappa backslash sigma S, where backslash kappa equals 2 corresponds to a 97.7% confidence level. The probability of detection, P backslash text det, backslash alpha, equals 1 backslash 5 backslash left, backslash frac S backslash text CL, plus backslash kappa backslash sigma s backslash mu backslash alpha backslash sigma s backslash right dollar decreases linearly with backslash alpha and drops to 0 as backslash alpha backslash to 1. We demonstrate this with a concrete example. A two-dimensional latent space, backslash zeta backslash eta, sampled from the Wigner function of a single photon Fock state. W1 backslash wrangle backslash zeta backslash eta equals backslash frac 1 backslash pi backslash left backslash x backslash left minus 2 backslash zeta 2 plus backslash eta 2 backslash right. This is a non-classical state. Its Wigner function is negative in some regions, a hallmark of quantum behavior. We probe this latent space via a family of linear readout contexts. Y equals backslash zeta backslash cos backslash theta plus backslash eta backslash sin backslash theta, analogous to quadrature measurements in quantum optics. For each angle backslash theta j, we discretize the outcome into bins and compute the marginal probabilities p, yk backslash theta j. The resulting forward matrix, A, maps the latent distribution to observable statistics. We then solve the convex optimization problem to find the optimal witness C, and compute backslash delta. The result? A clear violation of classical consistency. Nonclassicality is detectable even in the presence of moderate noise. To further validate our framework, we consider a quantum classical mixture. A density operator backslash rho backslash beta equals 1 backslash beta, 1 backslash wrangle backslash langle 1 plus backslash beta backslash rho backslash text th, 1, where backslash rho backslash text th, $1 is a thermal state with mean photon number 1. This preserves energy while varying non-classicality. We compute the detection probability as a function of both backslash alpha, classical admixture, and backslash beta, quantum mixing. The heat map reveals a robust region, well within experimental reach, where non-classicality remains detectable despite noise. But what if the latent space isn't continuous phase space? What if it's discrete? We show that the framework generalizes to discrete systems, such as spin systems. Consider a spin $J system prepared in a quantum state. Each readout context corresponds to measuring the spin projection along a direction, backslash math fen backslash theta. The outcome is coarse-grained, high activation or low activation based on whether the projection exceeds a threshold. This defines a binary POVM. Crucially, the activation probabilities can be written as P backslash tech stack backslash theta equals backslash int D backslash omega backslash W backslash rho J backslash omega backslash xi backslash tech stack backslash theta backslash omega. This is formally identical to the latent phase space representation we used earlier. So even in discrete systems, the same consistency test applies. And in the large $J limit, the spin system reduces to an effective harmonic oscillator via the Holstein-Primakov approximation, reconnecting back to the continuous phase space picture. This is particularly relevant for quantum biophysics. Many biological processes involve collective vibrational modes, vibronic degrees of freedom that could support quantum coherence. Now here's the revolutionary part. This test does not require us to assume that the brain uses autoencoders or even latent representations at all. It only requires that we can measure decoding statistics under multiple contexts. In a real neural experiment, this means use high-density electrode arrays to record population-level activity. Use optogenetic stimulation to define different readout contexts by perturbing specific subpopulations, modulating network states, or implementing closed-loop feedback. Then, for each context, estimate the probability distribution over neural outputs. The forward matrix $A is constructed operationally. Partition the input space into regions, estimate conditional probabilities P, YK, Z backslash and ZI, backslash theta J from independent data, and build $A without optimizing for prediction. This ensures the test probes cross-context consistency, not just predictive power. We also emphasize two key assumptions. First, that changing the measurement context doesn't alter the underlying latent quasi distribution. Second, that the latent structure remains stable over the measurement window. These are reasonable in many experimental setups, especially with stable cultures or organoids. So what does this mean for neuroscience? It means we now have a direct, experimentally accessible pathway to test whether neural representations exhibit non-classical statistical structure. No need to identify quantum hardware. No need to assume specific physical mechanisms. Just measure how neural activity patterns vary across different decoding contexts, and check whether all the resulting statistics can be explained by a single classical probability distribution. If not, then the brain's information processing violates classical consistency. And that would be a profound discovery. This work shifts the search for quantum-like signatures in neural systems from the microscopic level, where decoherence is a major obstacle, to the ensemble level, where statistical constraints are robust and testable. It brings tools from quantum foundations, contextuality, Bell-type tests, witnesses, into the realm of neuroscience and artificial intelligence. And in doing so, it suggests something radical, that the fundamental physics of biological intelligence might be revealed not by looking deeper into the brain's molecules, but by analyzing how its representations behave under multiple perspectives. Because sometimes, the most powerful test of reality isn't in the details of the system, but in the consistency of how we observe it.